Hello everyone. Since this is the first video of the tutorial series, let me give a quick introduction about myself. I am Abhijit and I am working as a software developer at Bank of New York Mellon. And during my college days, I had a keen interest in competitive programming, and I have been to the ACM ICPC regionals for a couple of times, and I am starting this video series involving all the which will cover most of the algorithms that are required to do well in the competitive programming websites. So the topic which I will be covering today is binary exponentiation. What is binary exponentiation? It's a simple trick to calculate a to the power n in big O of log n time, which is a major improvement if we follow the naive way of multiplying a into a like this n number of times, and the complexity for such an operation will be big O of n. So it's clear why we should use binary exponentiation over the naive approach, because it's super fast as compared to the naive approach. So now that we know the why, let's learn the how. So let me take an example to make things more clear. Let's take 3, which is raised to the power of 13. So the idea, as I said, the idea of binary exponentiation is that we split the work using the binary representation of the exponent. So we'll first represent the binary representation, the exponent in its binary form. So the binary representation of 13 is 1101 base 2. Okay, and this, as you know, is 2 to the power 3. This, as you know, is 2 to the power 2. This, as you know, is 2 to the power 1, and this is 2 to the power 0. So we'll be splitting this, and since this is 1 and the value over here is 2 to the power 3 in decimal form, so we can write 3 as 3 to the power 8 times, since this is a 1, so it will also count, so times 3 to the power 4 times, since this is a 0 and the exponent is 2 here, so it won't count, so we'll skip this and then we'll move on to the next position. And since this is 1, so we'll be taking the power of 3 into consideration, and 2 to the power 0 is 1, so here we get 3 times of 1. The exponent e equal to, in the binary representation of a number, it will have floor of log e plus 1 digit in the binary representation of e. So we only need to perform big O of log of the exponent times of the multiplications if we know the powers of the base. So if we know the powers such as 3 to the power 1 and 3 to the power 4 and 3 to the power 8, we can compute the multiplication by performing 3 steps. Only 3 multiplications will be needed here. Only 3 multiplications will be required to compute 3 to the power 13, as opposed to multiplying 13 number of times. So you can see, with the help of a simple example, we can compute it in almost 4 times the less number of computations that are required. because 3 into 4 is 12 and 3 to the power 13 is 4 times greater than 4 times of the required number of computations, which is 3. And this gap widens for larger numbers. So there will come a time where you won't be able to calculate the large powers using the naive method at all, but still we'll be able to find it using this simple trick. In general, to compute a to the power of n, we require a to the power 1, a to the power of 2, a to the power of 4, a to the power of 8, up till a to the power of 4 or log of n base 2. So using these powers, you can compute a to the power n in log of n time. So the only question that remains is we need to have a fast way to compute these powers. And if you observe clearly, each of the powers, each of the elements, as we move forward, is the square of the previous element. A square is the square of a to the power 1. A to the power 4 is the square of a to the power of 2. Similarly, a to the power 8 is the square of a to the power of 4. So the final complexity of this algorithm is log of n. We have to compute log n powers of a. So now that we have the idea clear, let me down a recursive relation to compute a to the power n, and we can also code this recursive relation. So a to the power of n, let's start with the base case. It's equal to 1 if n is equal to 0. If n is greater than 0 and n is even, it is equal to a to the power of n by 2 squared. This is for n greater than 0 and n is even, and a to the power of n minus 1 by 2 squared if n is greater than 0 and n is odd. Now that we have the recursive relation, we are in a good position to code it. So let's get started with binary exponentiation. I am going to write the recursive approach first. So long recursive binary exponentiation, and we take two parameters. One is the base and the other one is the exponent. And as you remember that in the base condition, when the exponent becomes 0, we return 1. After that, let's compute the result, and we will split the result into two parts, one for the odd part and the other the even case, when the exponent is either odd or the exponent is even. So we call the function recursively for a comma b by 2, okay, and later we can check if this exponent was odd, then we can simply return result squared times a else if the exponent was even, we can simply return the exponent, the result squared. Alright. Secondly, I'll write the iterative approach to the binary exponentiation approach. Okay. So we'll name it bin. We'll name it ITR binary exponentiation, and we also pass two parameters in this function as well, and we can initialize the result as 1, and we'll make computations till we have an exponent to multiply. So we'll be reducing b at each step. I mean, we'll be halving, we'll be reducing b to its half the value at each step. So while b greater than 0, and we'll check if b is odd, then we'll just multiply the base to the result, and then we'll square up the base and we'll divide the exponent by 2, and we'll return the result. So let's test out the results. So we'll call the first recursive approach, and for 3 to the power 8, and we'll also test the second iterative approach for the same power and exponent, and we'll check if they both give us the correct results. Result 1 and result 2. Let's just check the value which we should be getting, which is 3 to the power 8, and that's 6561. So now I'm about to run this code. So let's see if we get the value which we, yeah. So we are getting the value which we had just computed, 6561, using both the iterative and recursive approach.